synchronous generator is connected to 11 kV bus bar. It is given that a synchronous generator, some internal reactance, is connected to an infinite bus bar. What is the infinite bus bar? It is 11 angle 0 kV, and this is given as what? 0.8 ohms. This is 1.2 ohms, and this voltage is given as 15 angle delta. So we have to find what is delta. So what is given? The power delivered over here is 70 megawatt, right? So what we have to do here is that we have to use the approximated. So we are given what all values? We are given E is given. This is E, right? We are given E. We are given V. We are given X, right? And we have to find, and we are also given PE, right? So what is PE? PE equal to EV by X times delta. So delta would be inverse E X divided by EV. So if you do that, substitute the values, you will get it as 20 into 10 power 6 into 0.8 divided by 11 into 15 into 4 6. 4 6 and 4 6 cancels. If you do this, what value you will get? You should get this as 58.04 degrees. This is not per se a question from the stability, but yeah, you have to find. It's a question from stability, but it doesn't pertain to the stability limits. Just want you to find what is the load angle. This is more of a question from system operations. Clear? Are you guys here? Are you guys able to hear me? Oh, is it better now? Okay, so let's do the next question, right? A two-pole, 3 hertz, 11 kV, synchronous generator, has rating of we are given 60 megawatt the rating and the PF. Not audible at all? Am I audible now? Or is it really bad? So just let me know if I'm audible or not audible. Am I audible? Okay, good. Right. Yeah. So here we have a question where we are given that the generator is a two-pole generator, 50 hertz, 11 kV, and the power rating is 60 megawatt and 0.85 lagging, right? If the moment of if so this is one of those questions that is associated with transient stability. If the rotor moment of inertia is 8,800 kg meter square, then inertia constant. So they are asking you to find inertia constant. Can you guys attempt this problem? 8.1. So you're given a lot of details. This is a direct formula application, right? Can you guys try, or do you want me to solve it? Oh, so this is back today. So do you guys want to? Okay, you're trying. Good, good, good. So just to make sure that you guys are understanding this clearly, what is given? So given P is equal to 2, F is equal to 50, right? Then V is equal to 11, right? Then P is equal to 60 megawatt, and cos phi is equal to 0.85, and I is equal to, definition is equal to, right? What are they asking you to find? They are asking you to find the inertia constant, H. Let me know once you guys are done, okay? Are you guys done? Okay, right. So they are asking you to calculate H, right? So what is its formula? This is a simple formula for substitution. It is the kinetic energy stored divided by rating of generator, right? What is kinetic energy stored? It is half I omega squared divided by S, right? So we know I, which is given as 800, but we don't know omega. But what is omega? Omega is 2 pi f. Right? What is it is given as 50? It is 100 pi. So and what is S? S, we don't know S. We know P and cos phi. S is equal to P divided by cos phi. So if you substitute, you will have 1 by 2 into 1800 into 100 by the whole square divided by e into 10 power 6 divided by 0.85. Right? So if you substitute this, you will get it as 0.152 G per MVA or 6.152 second inverse. Second, right? C is the correct answer. Right? Now, is this clear? So there is a second part to this question. Second part to this question is they are asking you to calculate the moment in this one, right? So what is M? We can do it two approaches. M is SH divided by 80F, that is divided by, that is P divided by H divided by 180F cos phi. Right? So what do we have? So if you substitute this, you have 60 into calculated as 6.152 divided by 180 to into this 0.85. So we will get it as 0.04825. Clear? Okay. So the next question, this is steady state stability limit. You should be able to solve this, right? 500 megawatt, 11 kV, phase alternator. So they are asking you to find the maximum power transfer to an infinite bus. So you are given a 500 MVA, okay, 500 MVA, 11 kV three-phase alternator operating at 50 hertz. So you are given the power rating of the generator, the voltage of the generator, voltage of this second generator, and the impedance. So if you are given, how do you calculate SSL? Can you try this question? I've told you, given on what are the parameters that are given to you, you have to select the um, values. What is the value? MW. .2. Okay, how did you arrive with that? This is the steady state stability limit. Is given, it is EV by X, right? Maximum power transfer. Here it is given as 11. 11 divided by J 0.605. You should get 200. Do you know where it went wrong? right? Takura, is this clear? Okay. So the next question, right? So this question is, so you are given that H1 is 5 mg per MVA. So this is basically the kinetic energy stored divided by 5 with respect to this 500, right? And this 5 mg is with respect to 200. So they are asking you to calculate the total inertia. So the total inertia, if they have not said anything, we are assuming that they are swinging together. So the total H is H1 plus H2. So if they were in common base, you could have added directly, but they are not in common base and they are asking you to convert into a different base. First, what you have to do is that you have to calculate H1 new, the new base as H1, H1 old into old base divided by new base. Basically, we are calculating the kinetic energy stored with respect to this MVA and converting that with respect to the new, right? We will get it as 25. And what is H2 new? So basically, what we're trying to say here is, if they say their inertia constant in the new base, you have to convert the given H into with respect to the new base by multiplying this with its own rating and dividing it by the new rating, right? So H1 plus H2 would be, is this clear? So let's look at one question on a similar line, right? is 9. So there are two generating stations connected by tie-line. So station 1 has 4 identical generators having uh, rated 100 MVA and H is equal to 9 mg plus MVA, right? And station 2 they are asking you to calculate equivalent inertia constant of the system. We are asking you to consider these two generation systems together and calculate the inertia constant of the system with 150 MVA. So can you guys try this or do you want me to solve this? It's straightforward, but there is a small change from the previous problem, that's all. Earlier in the previous question, on one side of the bus there was only one generator. Here now there are 3 generators. First you need to bring them together, and second station you need to replace by an equivalent generator, then combine them. Good. 140, good, correct answer. Sakura, you got the answer? Okay, good, good. I don't have to solve this. Thank you. Okay. So the next question. Now we are moving into steady state, the angle, right? The angle type questions. The synchronous generator is a okay. You have a synchronous generator that has a reactance connected through a transformer, the transmission line. to a infinite bus bar, right? So the synchronous generator reactance is 1.2 pu. This is 0.6 pu. This is 0.6 pu, right? So the voltage of the alternator is 1.2 pu. The voltage at the infinite bus bar is 1 pu, right? And the H of the generator is given as 4 millijoules per MVA. Right? And the system frequency F is given as 3 Hertz. What you are supposed to calculate is calculate frequency of oscillation made by router made by the alternator made by alternator, and it is loaded to 80 percentage of steady-state stability limit, right? So I'll help you. Let's do this together, right? So first we have to calculate what the steady-state stability limit is. What is steady-state stability limit? We are given EV by, so what is E? E is given as 1.2, V is 1. What is X? 1.2 plus 0.6 plus 0.6, that is right. So that is 2.4. That becomes 0.5 per unit, right? Now they are saying at 80%, right? So 0.8 pm is equal to pm and delta. So if we do, we will get delta as 3.13 degrees. Now here is the part where we use the mechanical setup, right? So I think I will have to introduce you to the concept of so if it here we have to, let's diverge a bit, right? Here we have to look at this. How do we find the frequency of oscillation, right? So for that we need to find the solution for the swing equation. What was the swing equation? It was m into d square delta by dt square, right, is equal to ds minus dv by x in delta, right? So let's try to linearize this equation. So how do we linearize it? We take a small gradient. Now it becomes a linear differential equation. So if we do the differentiation, you will get m into del square by dt square into delta delta, because delta 0 is a constant value, and ps also will go away. It will become, because ps and p is initial condition, these two are same, right? You will get minus delta p, right? So if you rearrange this again, you get m into square by dt square delta is equal to minus delta pe, which is same as minus 2pe by rho delta delta 0 into delta delta, basically slope into the value, right? So if you rearrange this again, now we have a whole equation with respect to delta delta. This is basically a number, right? This is not to worry about. This is a number and is equal to 0. So we want to find the roots of the equation. So if you make d by dt as k, you will get this equation as mk square plus 2pe by rho delta equal to 0 into delta delta equal to 0. So if you solve this, you will get k as plus or minus 1 by m minus 2pe by rho delta delta 0 is to by 2, right? So this is the frequency of oscillation of the system. So we are asking to ask you to find the frequency of oscillation of the system. This is the formula that we go for, right? So now let's come back to the question. This question, given question, if we substitute, you will get it as equal to plus or minus 1 by m on the previous slide. Okay. Quantity square over k is okay. So yeah. So what is PE? We know as EV by X and delta. What is dou PE by dou delta at delta 0? That would be EV by X cos delta 0, correct? So if you substitute this as per the question, you will get it as 1.2 into 1 divided by 2.4 into of delta 0. Delta 0 is approximately 90 degrees. Since nothing is given, we are assuming that in no resistance, since the system has no resistance, we are assuming delta 0 would be approximately 90 degrees, right? So it would be cos 1. So you will get this as 0.5, right? And what is M? M is SH divided by M, right? So you would get it as 1 into 4 divided by so the K we are calculating is basically omega. So if you want the frequency in hertz, you need to divide that by 5. So what did we say K was? It is plus or minus root of 1 by M into dou P by dou delta at delta 0, right? So this is 2 pi F. So F will be this divided by 1 divided by 2 pi. So if you substitute the values, you will get it as by pi. Oh, sorry. The cos 90 is 0, my bad. Where is the difference? Yeah, cos 90 is 0. Sorry, my bad. I should say sin 90. So my bad is we are assuming delta 0 is 0 actually. Delta 0 is 0. My bad. Thank you for correcting me. So the assumption over here is since delta 0 is not given, delta 0 is, so the initial condition is true. I'll get back to you on this question. There's some issue with it for me. Oh, my bad. Delta 0 is not 0. Let me see. Delta 0 we calculated 53.13, right? That is 0.6. 1.5 into 0.6 minus 0.3. If you substitute it over here, you will get the value accordingly. My bad. Delta 0 we had calculated over here, right? Calculated as delta 0 is 53.13. I understand that that question is a bit confusing. We'll try one more question, right? This time we will make it straightforward, right? Calculate oscillation frequency when delivering 20% of in above question. So here we have to see 0.2 times max is max delta 0. If we calculate, you will get delta 0 as 7.5 degrees, right? So what is our dou PE by dou delta 0? Is EB by X equivalent of delta 0. Am I audible now? So let's look at two more questions before we go to the next topic, right? So 50 Hz 4 pole 500 MVA 22 kV turbo generator is delivering rated MVA at 0.8 PF. 0.8 PF, right? Suddenly, a phase fault occurs and output reduces by if input remains same, what will be the rating in mega Newton meter? So can you attempt this or do you need help? Can you hear me? Do you guys attempted this or do you need help? Hello? Okay. Go through your notes. Everything is most probably there. So I'll give you tell you what you have to find TA, right? And what is TA? TA is TA divided by omega. So basically you have to find the accelerating power and you have to find the omega and then you will have TA acceleration. So you have to find what PA and omega is. Pretty straightforward. Done. Okay. So what is given? So the original power output given is rated MVA. What is rated MVA? 500 MVA into 0.8. That would be 200 W. Now what is P2? P2 is reduced by 60%. So it will be now 40% P1. That would be 240 MW. PA would be 1 minus 2, that is 400 minus 240. That would be 160 MW. Now omega. What is omega? We're talking about mechanical rotation. It is 2 pi ns divided by, right? This is RPM, and this is, we are talking about mechanical omega, right? This is 160. That is where the mistake is. It is 160. 160 reduced by 60%. This would be 240. Correct? Thank you. So what is NS? NS is 120 by, so if you do that, 120 into 50 divided by 4, so you will get this as 1500 RPM. This is 2 pi into 1500 rotations per minute divided by 60. That will give you in seconds, radians per second. So 2 into so what is TA? TA is TA divided by omega. So that is omega what this is divided by, if you do that you will get it as Yeah. Why? It's 1500. This is not 500. This is 1500. 120 into 50 into 2500 divided by 60. Oh, 50 pi. Sorry, my bad. What did I do wrong? 3000 divided by 60. 50. Sorry, this is not 750. This is 3 pi. 40 divided by 50 divided by pi. We get correct answer is 1.52. My bad. Thank you. 1.52 is correct answer. Thank you. Thank you, Rakura. Right. We will do few more questions later. Right. Now let's proceed to the next topic. Right. Is this okay? Or do you want to do one or two more questions? Okay. Like spirit. Yeah. So they have said that the synchronous generator has a reactance of 1.35 unit. It's connected to a infinite bus bar with voltage 1 per unit to a transmission line having impedance 0.2 per unit. So this is the maximum output. So maximum output, steady state stability limit, and everything is the same. So there's a steady state. If the steady state stability limit has to be 1.2 per unit, what is the value of E? It's a simple formula substitution. You can let me know what the value is. Good. You will come as Varun, did you get it? The last question, right? This is also a nice question. Synchronous generator connected to a synchronous motor via a transmission line, right? So the H is and here here it is. So before fault, region is equal to so we are given this much detail. You are supposed to calculate the acceleration caused due to the fault. Can you guys try? 0.04. This is the angular acceleration, right? Tell me something. Okay. Sakura, are you done? Okay. So we are given that what is P1 per unit, what is P2 0.6 per unit. So PA acceleration would be 1 minus 0.6, that is 0.4 per unit, right? What is PA? M alpha, or M into rho square delta by rho t square. So we need to find alpha, right? So what is alpha? Alpha is PA by M, right? So what is M? M is S H divided by, since they have asked for electrical degrees, right? Not radians. Since if they are asking for electrical degrees, you use 180 F. If they are asking for electrical radians, you use 1 pi F, right? So we need to find what H is. So we know what PA is, which is 0.4. We assume S is 1 per unit, right? Then we know what is the frequency, that is 50 hertz, right? But we don't know what H is. That is where we have to go back to the question. So they have given that the two synchronous machines are not identical. So when they are saying it's not identical, means that they do not swing together. So if they do not swing together, what is the H equivalent? Is H1 2 divided by H1 plus H2. If they, in the question, if they say that it was identical, it would have been HEQ would be H1 plus 2, right? But since they have given that they are not identical, then they won't swing together. So we have to use this formula, right? So if you substitute H1 and H2, you would get 6 into 4 divided by 10, which is 2.4. So if you substitute that value over here, it is 0.4 divided by 1 into 0.24 divided by 180 into, right? So if you do this, you will get this as 1900 electrical degrees per second square. Now, yeah, 2.4, yeah, my bad. 2.4, right? My bad, I just put a mistake. 2.4, so you get 1500 electrical degrees per second. If in the question they had asked electrical radians per second, then you would have to use pi over here, or you could just multiply this by pi divided by 180. So this would be, yeah. Is that clear, Varun? Do you understand where you got the mistake? One more question. This is a very nice question. ठीक है. So generator with constant terminal voltage 1.0 per unit, right, is supplying power through a step-up transformer who has a reactance of 0.12 per unit to a double circuit line. So these are two parallel lines to an infinite bus bar which has voltages 1 per unit, right? So for this given system, the steady state stability limit is found to be 6.5 per unit. So now the question is, if one of the line trips, if one of the line trips, what is the new result? You are given this much, that the generator has a constant terminal voltage of 1 per unit. So you can neglect the reactance of the generator and the resistance and susceptance of the transmission line. They given this condition, what is the new SSL? So one of the transmission line trips. So there is a fault on one of the transmission line and one of the transmission line goes away. So under this new condition, what is the new steady state stability limit? Basically into a question, but yeah. Are you guys trying? Okay, good. Point one. Okay. So you got it? So 3.12. Okay. Let's see. So what is SSL? It is EV divided by X, right? So what is given? It is 0.25. E is 1, V is 1, and what is X? X is basically 0.12 plus these two in parallel. So that will be by 2. So if you substitute this, rearrange this, you will get excess 2 times of 1 divided by 0.25 minus 0.12. So you would get this as 0.08. So that is the reactance of one transmission line. So what is the new condition? Instead of both transmission lines, there is only one transmission line. So the new X effective would be 0.12 plus 0.08, it should be 0.2. So the SSL would be 1 into 1 divided by 0.2. Basically, it is a simple network question that they are asking you to find the equivalent resistance, right? So they are saying that first there is one line. So basically, this is what this question is at the end of the day. At the simplest rate, there is one resistance. What is the equivalent reactance of the system? Now this is R1, R2, R2, and they have given the SSL, so you find R2, and they are asking you to find, as simple as that. Clear? So do you guys understand where you guys made a mistake? It's extremely important to understand where the mistake happened, right? Okay. Let's move on to equilibrium criteria. So equilibrium criteria requires some amount of these are my notes. I'll upload this also to the. Is this clear? Visible? Is this visible? Are you guys able to read it? Okay, good. So let's go. Basically, I told you, like when we were looking at the swing equation, we said that there are two approaches of solving the swing equation. One was the equation-based approach, which we saw where we took the linear approximation, we found the k and the frequency of oscillation, all those things, right? And the second approach is to do it graphically, which is applicable for single machine system or a two machine system by considering it as two single machine system. So what equilibrium criteria says? It is actually a graphical approach, right? What it says is that the area covered by the synchronous machine between swinging points is zero. Or basically, the area, okay, now, suppose now we have this curve, right? So this is where the system is right now. Now a disturbance happens and the system starts swinging or oscillating. So the area made by the system in acceleration and deceleration during this swing is same. That's what we are seeing over here. The area of acceleration made by the synchronous machine is equal to the area of the acceleration during the first swing. Right? So what we have to do is that, so this is our swing equation, right? And delta square by dt square is equal to A. So what we are going to do is that we are going to try to solve this from an area point of view. So we multiplied both sides by this factor 2 delta t dt, right? And then we integrated the system with respect to delta t. So we multiply both sides by this thing and we integrate it with respect to delta t. So when we do that, we get d delta by dt is equal to 2 by n a d delta square, which is equal to 0. So basically, what we are saying is that when a system, this is basically the swing equation, right? What we are saying over here is, what we're saying here is that when a disturbance happens, the rotor rotates in a very similar pattern to that of the pendulum, right? Basically, what happens? At this point, acceleration is 0, but omega is equal to omega max. So this is our original condition. Then it starts swinging and it will go to the point where omega is equal to 0, right? And this is, it swings back to the point where again it becomes 0 and it comes back. That's how the, basically it starts from here, it goes, it comes back, it goes, it comes back, and it finally settles, right? What it's saying is that the area between this original point and the acceleration point, maximum acceleration point, and the this thing from the omega 0, this net area will be 0. This area will be equal to this area. So say at A, speed is 0 and is accelerated by gravity, right? At this point, it starts accelerating, and at this point, the speed is at maximum, right? But the gravity effect stops, but due to inertia, it keeps on going. So basically, even though the uh, effect of gravity is done over here, you keep on swinging due to what? Inertia. So due to inertia, this will keep going, but then due to gravity, there will be deacceleration. What happens at this point? The uh, acceleration gained due to inertia and the deacceleration offered by gravity becomes equal, and the ball stops here for a moment, or the oscillation stops here for a moment, that is omega is equal to 0, then starts swinging back, right? Suppose the fault, a fault happens at A, right? And then it is eliminated at B, but the system won't stop oscillating at that point. It will keep swinging towards C due to system inertia. There is rotating parts, so there will be inertia. So at A, speed is 0, but acceleration is maximum. At B, acceleration is 0, speed is maximum. Then due to the oscillation, due to inertia, this will continue. Is this clear? Okay. So now let's look at the initial condition. So this is the condition at this point A, right? What does it? PS is equal to P is equal to PM sine delta 0, right? So if we calculate delta 0, it will be sine inverse PS by PM, right? What is PS? PS is the condition value. What is PS? So initial condition. So it depends on how much power the generator is generating, right? So if you look at the curve, this is the maximum power the generator can generate, right? Or this will be our triple SL, and the system can operate at any point. It can produce 30%, 40%, 50%. So whatever that value is, this one, and this is our PM is our steady state stability limit, right? So delta zero will be our initial condition. So the oscillation happens between delta zero and delta, right? And at synchronous speed, this will be zero. So basically what happens when the oscillation happens, the angular velocity of the synchronous machine will not be synchronous speed, right? So but the area covered with respect below and above synchronous speed will be the same. So equal area criteria can be used to see if so if the areas are equal, then that means the system will be stable, right? If the area is not equal, if there is some difference, then the stability will be affected. So what we're trying to say is that using equal area criteria, we will find something called as critical clearing angle. So from the starting point, from delta zero, there is some angle up to which if the system swings, the area will be equal, right? And if the area is equal, then the system will be stable. That is, the fault has to be cleared before. Let's see from this example. This is delta zero. This is delta C. If the fault is not cleared by delta C, suppose this is swinging, right? If the ball is rolling from here, it starts rolling, 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 rolling. If the fault is not cleared at this point, if the fault is cleared at this point, then it will swing exactly the equal amount and come back. Then the system has a chance that it will be stable. But if the fault is not cleared by this point, then what happens? The area on this side and this side will not be the same. The area on this side will be less than greater than area on this side. So what happens? It will cause instability. So that is what we are trying to see next. So if area 1 less than area 2, then it is stable. If area 1 is equal to area 2, it is critically stable, and if area 1 is greater than area 2, it is unstable. So basically, if the fault is cleared, consider this blue as area 1, the area between delta 0 and delta C, and consider the area between delta C and delta max as A2, right? If area 1 is less than area 2, then the system will be stable. Basically, when the system started swinging, we clear the fault here itself. There is plenty of time and space for it to swing and come back. So it will be stable. If area 1 is equal to area 2, then it is said as critically stable. It will keep on swinging, but this will come back. But if area 1 is greater than area 2, there is not enough space for it to swing. What happens? It will swing beyond delta max and it won't come back. If you look at it from a sine wave point of view, okay, sine wave point of view. So this is Pm versus delta. So this is P delta, right? So now suppose the system is now operating at this condition. So this is our mechanical power and this is our electrical power. So this is the current situation and this would be our delta zero and this would be our delta. So if the system starts swinging, right, this area has to be less than this area. We will look at that. This is what we were talking about. So suppose the mechanical input suddenly increases. So this was the system operating condition, right? So suppose this is our system operating condition. System is initially at PS1 and this is delta zero. Now suddenly the mechanical input increased to PS2, right? So suddenly the mechanical input increased to PS2. So this should correspond to a this will cause an acceleration, but it won't stop over here. It will start swinging further, right? So basically, even though this, so suddenly the mechanical input changed and the electrical operating condition also shifts accordingly over here, but it won't stop over here. It will keep swinging. It will keep swinging and it will keep swinging and it will go to a point where the omega becomes zero and it will start coming back. Right? And the area between this and the area between this, if they are equal, then that is critical. If area 1 is less than area 2, then it is good, it is stable. But if area 1 is greater than area 2, then it will become unstable. Basically, if area 1 is less than area 2, what happens is that this point goes over somewhere over here. So if it goes beyond 90 degrees, it becomes unstable, right? If you remember. So the big deciding factor is delta zero and the point where the new condition exists. So here it is the new mechanical input. This could be also the point where the fault gets cleared. So this is the new steady state point, but it won't stop over here. It will start oscillating. So if the area from the old operating condition to the new operating condition is less than or equal to the area from the new operating condition to the maximum point, then it will be stable. But if the area between the old operating condition and the new operating condition is greater than the area between the new operating condition and the steady state stability limit, then the system will lose synchronization. Is this clear? Does that make sense? Okay. So what I'm going to do is that there is lot with equal area criteria, which we will continue in the next class. So right now I'm going to stop this over here, right? I want you to go back and look at questions from stability in your previous gate questions and come back in the next class. I think we have a class on Saturday. So in Saturday we will finish equal area criteria and then we will proceed to economic load dispatch, which is a new topic in the syllabus, right? Are you guys with me so far? So I'm going to stop this over here. See you in the next class. You have to start looking at questions, right? Because given the time limitation, there is so much so questions that we can cover in the class. We need to do more questions, right? It's extremely important for gate.